It's my great pleasure to join the Presec ML seminar and to give the talk today. So today I will share with you our recent research on the security pitfalls or the security vulnerabilities of the DNN watermarking on the neuron obfuscation. And this is a joint work with my mentor student, Yifan Yan, and my supervisors, Professor Mi Zhang and Professor Min Yang at System and Software Security Lab at Fudan University. Okay, so in the past several years, one of the themes in my research is about to reduce the AI security problems to the neuron states. Some of the unsafe neuron states, especially like the neural invariance that I will introduce today, and also like the neuron redundancy, neuron exclusivity, and neuron activation. The theme is mainly because I try to view the problem of the AI security at a very microscopic way. That is to find out the bugs of the AI system at the neuron level. So these works are mainly about model protection and the data privacy. Today's talk, I will focus on the first part. It's about model protection. And in this work, we find 9 of the state-of-the-art white box DNN watermarking can be cracked with very basic level neuron invariance transformation. Okay, so what is the neuron invariance? Maybe some of you have heard it before, but I will just go back to the very beginning of the neural network and to understand how such invariance emerged in the development of the deep learning. So basically, the neuron is an element, or just one of the most basic elements of the deep learning, just like the 1958 Rosenblatt, who developed the neuron circuit, which is just like a mess, but it is very useful and also marks the very beginning of the deep learning. So he used this digital circuit to build up such a neural network. And in 1943, actually, McCulloch and Pitt has already formulated the idea of the neurons in the form of the perception formula, just as the formula here shows. The y equals the sigma and wixi, the summation, and plus b. This is a very simple formula, and all of us maybe know it when we just learn the deep learning or the artificial intelligence. Actually, we can see here the sigma is the activation function, and the inner part is just a linear layer. Okay, so the activation function can be chosen in very different ways, but in the popular neural networks, in most of the popular architectures like the ResNet, the VGGNet, or just like other visual models, we usually use the ReLU neuron because it is very numerical stable. Therefore, we can just briefly give the definition here, the ReLU function, which just output the original input if it is greater than 0. Otherwise, it will just output 0. And such a property will just make the ReLU neuron to divide the input space into 2 parts. One part is inactive and the other part is active. Therefore, with such a definition, we can just put it into the definition of McCulloch-Pitt's perception, and we just write out the definition here. So it is just one neuron. The neural invariance won't happen if there is just one neuron, but if we just compose all of these neurons into a very complicated neural network, then we'll find many different types of invariance properties. So let's see. If we just to concatenate one neuron and the other to let the output of one neuron as the input of the other, and we can get a deepened neural network. It is just a 2-layer. It's very simple and toy, but we can see some very interesting things here. The scale invariance just emerges from such a composition. What is the scale invariance? So many of you may know it before. It is about we scale the weight of the previous layer, just like the x here. We just scale it by 1 over lambda, and we put another lambda before in the next layer, the weight of the next layer. So just like the A here, then we can see a very magical thing happens. but it is just mathematically equivalent. Just we introduce such a scale factor lambda, and we just modify the weight. We can get a functionally equivalent neuron as the previous one. So this is a scale invariance. And the other one is a parallel neuron circuit, which means that we do not just deepen the neural network, we try to widen it, which means that we put the neurons in a vector and we get a neural layer. And we will see there's another type of the invariance property, which is called the permutation invariance. So we can just think about it. We pick up the first neuron, for example, above the screen, and we just transpose the position with the second neuron, and we can just make a shuffle, and therefore we get a neural network, but the output will not be changed due to such a permutation. So underlying such a property is actually the commutative so it's just because y1 plus y2 equals y2 plus y1. So the summation is commutative. Okay, so it just introduces a permutation invariance. So let's see why these types of invariance is important to our study of the AI security, especially our study of the security of the neural networks. For example, let's take the work by Ganju et al. At CCS 18, the Dataset Property Inference. I think many of you have read it before. So in this attack, the attacker would like to infer whether such an AI model is trained on a data set that satisfies some property. So for example, a face data set. We would like to determine whether the model is trained with all the faces has wear eyeglasses, for example. And we know that in such an attack, such a property inference attack, the attack model will will get the parameters of the AI model as the input, and to do a binary classification. So on whether there is a property or does not satisfy the property, right? Therefore, we can find something interesting. The AI model, the parameters of such a DNN model may satisfy the shuffle invariance, the permutation invariance, and the scale invariance. Therefore, if we train an attack model which is unaware of such invariance, then if the defender, for example, just shuffle the parameters in the original AI model, then the attack model will be mitigated, because if we again to input the shuffled weight into attack model, then the output will just be changed. This is what the invariance property means. It will just break the attack process, or just to break some defense. And we will see our work is mainly based on such an idea. So let's just do some more formal definition, for example. So what is invariance? We say some function f over the d-dimensional real valued space. And if there is some transform G over the input space, then we can say such a function is invariant over such transform G if we apply the transform G over some x, the fgx equals fx. It's very mathematical definition, but we'll find it's very useful. And for example, just a normal distribution, and we know that it is invariant over the z-axis, which actually means that it is invariant over some rotation matrix, some rotation transform over the z-axis. Okay. Therefore, let's just give one slide which summarizes what the relation between the DNN invariance and the attack and defense model. So up to now, we already know two types of invariance. The first one is the scaling invariance, and the second one is the order invariance, or the permutation invariance. If we just consider the edge layer fully connected loop neural network, then we can say the scale invariance need us to apply the lambda 1 to lambda h, the edge scale factors on the weight and the bias. And only if such scale factors are all positive, and they multiplied to be 1, then the output of the function will not be changed. This is a scaling invariance. And for the order invariance, it is the same, just to consider the permutation matrix over all the weight matrix and all the bias here. Therefore, combined with the example we discussed about the property inference attack, we know that only if the attacks and defense on the DNN does not satisfy the above invariance, so about the scaling invariance or the order invariance, then we can mitigate and crack such attack defense, or just mitigate such attack or crack such defense. And our two works will just, I will just use our recent works to demonstrate and to validate this point. So the first one is about our work published in the KDD23. So it's about to use the parameter obfuscation to remove the white box DNN watermarking. And it's mainly used the scale and the permutation and also some new invariance. Okay, so before I will briefly introduce what is the digital watermarking. The digital watermarking, and it's a very conventional idea. So just like the digital image here, we can see here is two types of watermark. The first one is the invisible watermark. So we just used a camera. It is mainly done by some very steersy encoding scheme or just by some deep neural network. We can just encode some message into the input image. And we can use some decoder to extract the watermark message from the image, right? And the other type is a visible watermark. It's very easy to see just just like a stamp at the image. And recently, we know that deep neural networks are requiring a large number of like the GPUs, or it just requires a large amount of well-annotated data and also tweaked learning algorithms. So the deep neural network is becoming an indispensable part of the intellectual property of the model owner. Therefore, we need to also consider the protection of the DNN watermark deep neural network in a more active way. So actually, the DNN model is facing stealing. For example, like the Trump et al.'s work in 2016, they found out that the attacker can steal the model from some machine learning as a service from the cloud, just by distillation from the cloud. And the other type of attack can happen at the end devices. So recent work in the 2021 at Unix has found that the models at the end devices, the 41% of such models are not protected, are not even encrypted or just enclosed in some secure places. Therefore, the attacker can steal the model from both the cloud and from the end device. And after that, the attacker will not just sell the model without any modification. So he may use some ownership obfuscation, like the pruning, the fine-tuning, the distillation, to make the model not look like the model before. Okay, so therefore, if we would like to protect and to verify the ownership of this owned model, we need to do the watermarking. And in the development of the DNN watermarking, basically from the 2017 and up to now, there are two types of the DNN watermarking. One type is the white box watermarking. It is mainly embedded in the internals of the DNN model. So for example, embedded in the weight or the activation values of the DNN model. Like we just encode a model of Fudan into the target model, then we can use some decoding algorithm to extract the message from the weight of the target model. And if we would like to verify whether a suspect model is stolen from us, then we can just also try to run the decoding algorithm over the suspect model. And we will find out, oh, the output is just like, it's very similar to the original message we embed. Therefore, we can say the model is stolen from us. And the other type is the black box watermarking, which is mainly studied from the 2018 by Adi et al. And it is mainly, it's kinds of the backdoor attack at the deep neural network. It is based on a verification set, and the embedding process just try to train the model so that it can memorize the input and output relation between the verifications, the samples in the verification set, and the target labels that we specify for the model. Okay, so if we would like to verify whether a suspect model is stolen from us, we just try to input all of these samples from the verification set and to see whether the output is expected just as we specified before. This is a black box one. And in this work, we will mainly study the white box watermarking because there are actually, if we just survey the recent literature, there are a large number of works that's published at the top-tier conferences about white box watermarking. And we find the robustness is a real concern. And therefore, we try to alarm the researchers and the users about the vulnerability of these white box watermarking schemes. Okay, so let's see one of the earliest white box watermarking is developed by Richard et al. At the ICME 17. So it's a very classic watermarking algorithm. And in the following, I will only introduce the process of the watermark extraction because our attack only need to do with the watermark extraction process because the embedding process is happened and is conducted by the defender. Okay, so it's conducted by the owner. So we just interested about the watermark extraction process. Let's see. The Uchila et al. Mainly embed and extract the watermark message in some of the convolutional kernel. So for example, such a convolutional neural network extracted the kernels at the first layer, and he will just do some pooling to get a flat vector. And there in the extraction process, there is a secret matrix, just like a secret key in the symmetric encryption schemes. And he will use the secret matrix to multiply it with the flat vector W here. He will get a vector, and he uses sigmoid to convert such a floating point value vector to a bit string 0101001, for example. Okay. This is the extraction process, and we may memorize it for a second because we will use some properties to attack it. So what is watermark removal? It is about to remove the watermark from the protected contents. So for example, if we would like to remove the watermark from the digital image, like the visible one, we can just add a white pad over the stump here, and we will find that the watermark is being erased or just be covered. And for the invisible one, it's actually more challenging because if we only add some white pad over the digital image, the message will not change radically. So for example, the message will change to message, but it will not radically hurt the matching rate between the original message, the message, and the message. Okay, so what the attacker expects in a removal attack, there are many different dimensions. So for example, we need the watermark is gone, and we need the removal is not expensive. We also need the original quality of the content is preserved. Okay, so we try to systematize these requirements, and we will get such a axis. There are different axes, and some of which may just have a trade-off with the other one. For example, we need the attack efficiency, which is the computation we need to do to remove the watermark, and also the utility loss, which is also another type of trade-off, because we need the model to remain useful even after we radically change the parameters or just change the weights of the neural network. And also the watermark verification success rate. So it just reflects the effectiveness of our attack. We need to remove the watermark, which means that we want to reduce the verification success rate to just fully random. And also the attacker's knowledge. So there are many different types of definition for the attacker's knowledge, like whether there's watermark in the model, or where is the watermark, or what type of watermark. Okay. So the removal tag can be measured in these different ways. And maybe there are also the tag robustness. So whether the owner can still recover the watermark, whether after our removal. And I would like to, so this slide just summarizes or just to give an appetite of why the DNN Invariance is important for the watermark removal. Because let's see, the DNN Invariance just gives us a very useful tools to radically change the parameters and also to change the internals of the neural network, while we can provably preserve the functionality of the original neural network, because it is invariance, right? It is literally means we will not change the input-output relation between the of the neural network. Therefore, it seems like there is a dilemma between the watermark verification success rate and the utility loss. But actually, in our 2 papers, we proved that there is no such trade-off. We can simply remove to reduce the watermark verification rate to fully random, while the utility of the model is preserved. Okay, so just as the formula here shows. Okay, and this is actually our work first time reviewed this point, and the previous attacks like the fine tuning, the retraining, or some other types of attack all need to reduce to trade the utility loss for the watermark verification rate. And here's just a slide to scientifically define and how to determine whether the watermark is removed. So in the literature, there's mainly the definition. We mainly use the definition of the BER, or called the bit error rate, because we just in the previous slide we say that the message of a watermark is usually a bit string. Therefore, if we try to determine the matching rate between the original model and the suspect model, we could just compare their watermark message. So for example, for the original model, the BER is usually 0, which means that they fully match each other. And for an independent model, which means that the model is not related with our original model, then the BER can be very high. For example, 80% or even 100%. Therefore, we can define the BER just as the matching rate between the bit strings, the extracted bit strings, and also the embedded bit strings. And in the SNP22 SOK on the watermarking messages for the watermarking schemes for the image classification models, the Lucas et al. Had defined the scaled BER, which is also a more effective and more fair metric for measure whether the watermark is moved. And it is mainly based on to scale the BER with some threshold, like the theta tilde here. The theta tilde is mainly the average BER of M independent models that is irrelevant with the original model. So with such a scaled BER, we can say only if the scaled BER is greater than 50%, then we can assert that the model watermark is removed. So we know that the scaling and the shuffle is invariant, is the 2 invariance attack in the 2 invariance transforms, and we can just try to think widely. So we can just apply the rescaling and also the shuffle over all the layers in the neural network, right? You can just apply the shuffle, randomly pick some neuron in the neural network, and to scale the incoming weight and the outcoming weight. And we can just, in this way, we will just maintain the functionality of the model while we can just modify the parameters. And we can also shuffle to change the row order in the weight matrix. And we can see only such a random apply of the scaling and the shuffle, we can reduce the verification rate, just to increase the BER to over 50%, the scaled BER, which means that the watermark is removed. Therefore, we can see that only if we know the invariance attack, the neuron invariance properties, and we can apply such invariance transform or the invariance attacks, we can just to achieve an optimal trade-off, or just there's almost no trade-off between all of these axes, like the utility loss. It is probably none, and attack efficiency, because the shuffling and the scaling only needs some scalar computation, so it is more cheaper, like than the fine-tuning or the retraining. And for the attacker's knowledge, we do not need to know where is the watermark and whether there is a watermark. We can just try, just to give us a model, we can just do such shuffle and rescaling randomly. And for the watermark verification success rate, we can just do it repetitively, and finally the scaled BER is over 50%. Okay, so we already know. So in the previous slides, we already know that the first watermark proposed by the Uchida et al. in 2017 is vulnerable to such attack. And we're really curious about, after about 6 and 7 years development, whether the following white box watermarking schemes have the same limitation. And unfortunately, it is true. And this slide just details about the previous removal attacks. And I will just skip this part. And if you are interested in this, you can just read it in our paper, and we analyze all of these types of previous attacks. And they are somehow limited in one or at least one of the dimensions we draw in the previous slide. Okay, so from the 2017 and the Uchida et al., we just try to systematize our attack, systematically evaluate our neural invariance attack over the another eight mainstream white box watermarking schemes. And we can just try to divide these watermarking schemes into different types. So the Uchida et al. Is just embed the watermark in the weight matrix. It is called weight-based. And there are also other types like the activation-based and also the passport-based. And we will just I will try to briefly introduce their mechanism and to analyze why these other types of watermark also suffer such a common vulnerability. So for example, there's two types of the very state-of-the-art weight-based watermark scheme. So it is like the followers of Uchida et al. They just, again, extract the convolutional kernel, the WI here. And the rigor just to try to use another deep neural network as an extractor. So he does not try to use some secret matrix, but he used another deep neural network to extract the watermark. Therefore, only if, because such a deep neural network is not invariant over the invariance in the protected model, therefore the watermark will be just to be randomly changed only if we just do shuffle or scaling over the original neural network. And also for the greedy residue, because there's again some just like the matrix multiplication and also the summation and some pooling and reshape. This procedure does not satisfy the invariance in the original neural network. Therefore, the base string, the output base string here will be arbitrarily manipulated if we just change the order and the scale of the WI. And here is the result. Okay, and for the activation-based, so we can just again think about the neural invariance, like the shuffle and the rescaling. We can such invariance not only just influence the weight matrix, it will also influence the activation vector. So for example, if we just to transpose to just shuffle the neurons in one layer, and the activation vector will also be shuffled, right? And in the deep science design, so another one representative activation-based watermark, he tried to have some verification, to choose some verification samples, and he gets the activation vectors from the protected neural network. He tried to embed the bit string, the watermark message, in the Gaussian mixture modeling centers. So called the Gaussian centers. We try to embed such messages into the center of the activation vectors. And again, we try to use the Widened approach to use some secret matrix to multiply with such center and to get a bit string. Therefore, we just do some shuffle and do some scaling. The activation value will be changed, and again, the watermark message will not exist in the obfuscated model. And the final part is about the passport-based watermark. So it is like a hybrid type between the weight-based watermark and the activation-based watermark. So actually, the deep IPR tried to embed such a message in the batch norm layer of the neural network. So just we can see here, the batch, he defined a kind of the passport layer, just as the definition here shows. The passport layer is just like the gamma is some scale vector, and it's just a dot product with xi and plus some beta, some bias. And he just tried to insert some passport layer into original neural network. He gets such a passport-based neural network. And let's see how the passport layer is important for. So let's see the verification process of the passport layer. It is the watermark is mainly embedded in the scale vector here, the gamma here. So he just tried to embed the watermark in the sign, the bit string of the watermark in the sign position of the gamma. So just we take the vector here, the gamma as a vector, and we just extract the sign, and we can get such a bit string, right? And let's see, such a simple layer seems there's no invariance, but actually there is, because the xi is another output, the output of the previous layer. Therefore, we can expand the xi at the just in the following form, the wi minus 1. So the output from the previous layer, and we just insert such a representation into the definition of the passport layer, and we can just write out such a formula, right? So because the deep IPR or the passport-based watermark embeds the watermark message in the sign position, then we can just try to use a new invariance called the sign invariance. And let's see, because the formula here, the formula in the center of the slide, we can just try to flip the sign of the gamma vector and the wi vector, and we will see the output of the passport layer will not change. Therefore, we can again preserve the functionality of such a passport-based neural network, while we can just dramatically change the watermark message in the sign position, because we just flip all the signs here. And here is the result. And okay, so this is the first part. So we use the parameter obfuscation, like the order invariance, the scale invariance, and the sign invariance to do the removal of the white box watermark. And this just reflects the common vulnerability of these designs of the white box watermark. They did not consider the characteristics and uniqueness of the deep neural network. Therefore, because there is some invariance, we can try to change the order to rescale the weight matrix and to flip the sign. Then the watermark message can be arbitrarily changed. And for the second part, I will just briefly introduce this part, and you can just hear more detailed one at Usenix Security 23. So it is another type of the obfuscation or the invariance, which is called the structural obfuscation. So it is not just about the parameter matrix, it is about architecture. Let's see, again, analyze the earliest one, the Uchida-Torres watermark. You can see here, there is actually a very tricky point. He used a secret message E, which is a fixed one, to be multiplied with the flattened convolutional kernel W here. Okay, and it is actually very, it cannot tolerate any fault. So what do I mean? It means that if we change the length of such a weight vector, or just the size of the kernel, then we can see the verification process will just meet some execution, to just meet some shape error, for example, in NumPy. Okay. So if we try to restore the correctness of such a program, verification program, then for example, we need to select the top K values from the weight vector, and to restore the executability of the verification process. But is it good? So actually, this reveals another type of vulnerability, which is the vulnerability against structural obfuscation. The analysis about the Uchida et al. In the previous slide inspires to define the idea of the dummy neuron. So what is a dummy neuron? So again, literally, it is about some neurons that we can add to some neural network without changing the functionality of the neural network. There's a very toy type, the dummy neuron or DN. So it is just add some neurons with incoming weight or 0, or outcoming weight also 0 here. And in a fully connected neural network, it's just like to insert 2 neurons, while in a convolutional neural network, it is like to insert a full 0 kernel into one convolutional layer. Okay. But this is very, it is not scarce at all, because there's all 0, and we can do some pruning to remove all of these dummy neurons. So this is toy one, but we can actually make the construction of the dummy neuron more complicated, and we will get more robust dummy neurons into the network. So, but actually, I will again highlight one point. So if we just insert such dummy neurons into the neural network, most of the watermarking process will just be cracked, because they are intolerant against such faults. Okay, so here is some construction of more complicated dummy neurons. The first one is the neuron clique. The neuron clique means that we can try to insert a group of neurons which can cancel each other out in the neural network. And this such type of construction of the dummy neurons can be done by consider the property we need to maintain. So for example, at the right top here, the original problem is that we try to insert, for example, 2 neurons that they can cancel each other out. So we can write out such an equation, and we try to find out some W1, W2, B1, B2. They satisfy such an equation, and actually do some derivation. We can find out the first equation, the first construction we need is the output weight of the neurons will cancel each other out. So just like the 3 red dummy neuron here, the outcoming weight, the W1J, W2J, and W4J, we just should cancel each other out to get 0. Therefore, they will not contribute to the channel in the next layer. And the other one is about activation identity, which means that the incoming weight of the dummy neurons in one group should equal to each other. And the final one is the scaling positivity, because we do not, again, leave some exploitable traces for these dummy neurons. So for example, we do not want the incoming weights of the dummy neurons are all equal to each other, then we can just do the rescaling. Just in our previous paper, we can just add some lambda1 and to scale the UI1 with lambda1, while to cut down the outcoming weight by lambda1. Okay, and we'll again get a equivalent neural network. Another one is about neural split, which is similar to the previous one, but it just not insert 3 neurons that can cancel each other out. It just split one original neuron to several. And we can just intuitively think about how this can be done. We can just use some replacement identity, which means that the outcoming weight of the dummy neurons should equal to the original one. And finally, there's also the kernel expansion, also to change the shape of the original kernel. So for example, we can just pad the dummy neurons so that the padded part of the 3 dummy neurons, for example, can add to be 0. Therefore, the kernel padding can just again change the shape of the feature maps of the original model. Therefore, there's the full pipeline of the DNN obfuscation. We can try to use the neuron click, the neuron flip, the neuron split, and also the kernel expansion to construct such dummy neurons into a neural network and try to inject it into each layer of the neural network. And next, we'll use the parameter obfuscation to try to scale the incoming and outcoming weight and to shuffle the positions to mix all of these dummy neurons into the normal neurons. And finally, we can use the kernel expansion to further camouflage the shape of the feature map and also the weight matrix. And therefore, the obfuscated model will not look like the original model at all. And again, none of the previous white box DNN watermarking schemes can survive after such radical obfuscation. Okay, so finally, I will discuss some interesting points, which is also pointed about the reviewers, and they're also very interested about such a new technique and its relation with the program obfuscation. Because in DNN obfuscation, we try to use such a technique to preserve the functionality of the obfuscated neural network from the original one, while to remove the watermark message. While in program obfuscation, it is more like a protection of the intellectual property of the software writer, because program obfuscation try to fight against the anti-decompiling. So he or she does not want the program to be compiled. So there will be the change the variable name and also to obfuscate the control flow. It is quite similar to our DNN obfuscation techniques, and you may just think about it or discuss it. And the other one is whether such dummy neurons or also the parameter obfuscation can be detected and be recovered by the model owner. So it's actually a very interesting and also very important question for such watermark removal attacks. Actually, we analyzed this problem under different types of defenders. So for example, if we consider a defender who does not know how the dummy neurons are constructed, and he may just try to detect these dummy neurons via some anomaly detection technique, for example, and our analysis find out he cannot determine the dummy neurons from the normal neurons, because we do the scaling invariance, and we also do some rescaling to try to make the incoming and outcoming weights of the dummy neurons similar to the original ones. And for a stronger defender, so for example, the defender is very familiar with the construction of the dummy neurons, and we analyzed that it can use some property of the dummy neurons. For example, because the 2 dummy neurons in one group need to have at least incoming weight parallel to each other. Therefore, he can just check the cosine similarity between the weight vector of 2 neurons to check whether there are dummy neurons in the same group. Actually, this can be used to detect the dummy neurons, but it requires some computational cost, and also even after such removal, we cannot recover the watermark message because there are still the parameter obfuscation. So there is still the scaling and the shuffling in the neural network. And our analysis in the paper has proved that such scaling and shuffle cannot be recovered. Okay, so let's just give a take-home message. In our talk, from the very beginning, so it is about the neural invariance, and we analyzed the parameter invariance, just like the scaling, the order, the sign, these types of invariance, and also the structural invariance. So we try to insert some dummy neurons that will contribute nothing to the prediction behavior of the model, and we use these inner properties of the deep neural networks to understand the vulnerability of the existing white box DNN watermarking, which I think is very alarming because we need to rethink about the vulnerability of these newly devised algorithms and try to find out a more robust way for the protection of the DNN model. And also our other works also use such ideas to try to start from microscopic way to analyze the neural states to understand some other attacks like the data reconstruction and the property inference, some other attacks about data privacy. So you're welcome to read our other papers. And thanks for watching. And here is the link to the two papers I introduced today. And also you can also scan the QR code here to read more research about AI security from our group. And thank you. And if you have any questions, please just drop me the questions.